It's really a pleasure. I'm sorry that I guess none of you are together, but I'm sorry that we can't be in the same room together. And I know that all of you are very busy professionals with your careers. So it's wonderful that you are all here, and it was my pleasure to be able to provide some lectures. So I wonder, I came in on the tail end here. I wanted to say that I thought that was an excellent choice of an article, a very timely article on COVID that I think you just reviewed. But I wondered in terms of maybe if I could ask if you have any questions about the use of logistic regression in your research endeavors, and maybe pick up with any questions that you might have had after reviewing this journal article with Dr. Shaileja, and also then going through the lectures.
Dr. West, this is
Yes.
Nishad. I'm an neonatologist. About the article that Dr. Shaileja presented, they mentioned that they had checked the linearity of the predictor with respect to the logit of the. So how is that done?
Yeah, that's an excellent question. And so, and shall I use, I don't have it right in front of me, the article, but shall I use age as a covariate as an example to talk about how we would go about doing that?
Yeah, sure.
Okay, so when you do perform a logistic regression, the assumption is that the continuous covariate has a linear relationship with the log odds. Just like when you looked in simple linear regression, the average or the expected y was meant to have a straight line relationship with the covariate. If not, then you would break it into age groups, or dichotomize age. So the question was, what do you do in terms of checking linearity? So this is going to be a little bit cruder since I'm doing this, but we have the log odds. And remember that the odds is the probability that y equals 1 divided by the probability that y equals 0. And our assumption is that there's a linear relationship between log odds and age. And so the question is, how can you make this check? So suppose we had, say, 5-year age intervals, and what we would assume is that the slope as we go between each age interval is going to be equidistant. So what we need to do with the logistic regression is, for example, here's our coefficient. So I'm sorry for how crude this is, but the coefficient. And so if we have, if we take our continuous age and made it into 5-year age groups, so I'm going to make these up right now, 50 to 50 up to 54.99, 55 to 59, 60 up to 64.99. So we have equidistance age groups. So maybe I can ask Dr. Nishad and others, if we had only 3 age groups, then we would set up indicator variables. And I can talk about indicator variables if those have not been mentioned yet, Ashish. So Dr. Ashish, let me know if that has been mentioned.
Yes, you could talk more about it. We have not talked about indicator variables yet.
You have not talked about indicator variables. Okay, so I will briefly say here we have 3 age groups that we created from a continuous age variable. And so with indicator variables in either a linear or a logistic or a Cox model, in any of our generalized linear models, we would set up what are known as indicator variables to help us make comparisons. So the idea is that if you have P categories, and in this case, we have 3 categories, you always create P minus 1 indicator variables. So I'm going to create then, since there are 3 categories, 2 indicator variables, X1 and X2. And the way we set this up is that the we'll let X1 be 1 if the individual's in the second group, 0 otherwise. Then we will also set X2 to be 1 if the individual's in the highest age group, 0 otherwise. And now we're going to look in this other direction, and we'll see that if we have both indicator variables being a 0, what age group does that represent? Anybody like to just say which age group? 2 zeros means the individual's in 50 to 59. If X1 is a 1 and X2 is a 0, then that individual is in age group 55 to 59. And if it's 0, 1, then this individual is in age group 60 to 64. So I'm hoping that makes some sense, because now if we only had age in our model, in order to check this assumption of linearity with a continuous age, we would write log odds, and it would be B0 plus B1 times this indicator variable, X1, plus B2 times X2. So we end up getting a comparison between the middle age group 50 to 59 versus 55 to 59 versus 50 to 54 by this coefficient B1, and a comparison of 60 to 64, 60 to 64 versus the baseline of 50 to 54 with B2. And so basically we have two coefficients now that are making a comparison of an age group to group 1, the baseline. And if this difference was equidistant, so if I had even more, 65 to 69, 70 to 74, etc., what we would check, and this is the check. So Dr. Nishad, I hope this is helpful. We would have to categorize, set up these indicator variables, and check to make sure that the distance, the difference, numerical difference between each group in these coefficients was the same.
Would you look at the numerical difference in terms of the coefficients or in terms of the exponentiated coefficients, the odds ratios?
No, that's a great question. You would look at it in terms of the coefficient, because of the fact each of these coefficients is a log odds ratio. And so, and our goal is to make sure that the linearity of this continuous relationship is between log odds and age, because we're saying the log odds ratio is the same unit difference with each year of age. And our double check is by checking that the difference in log odds between one group, 55 to 59 and 50 to 59, is the same as between 60 to 64 and 55 to 59, etc. So it's literally a comparison, a rough comparison, that the differences between the coefficients are the same.
Thank you.
So great question. Thank you for asking it, because we could have a situation where it's not linear with age, right? It might increase with age. It might, be a curvilinear relationship and not a linear relationship. So thank you for that question.
Can I ask you one more question?
Absolutely.
I watched the videos that Dr. Ashish had shared, and they were really very well explained. And you had done a few post-estimation commands after running the logistic regression command. So my question is, Stata has a huge list of post-estimation commands that you can run. And how did you choose which ones to run? And does it depend on the situation?
So it does depend on the situation. So if we were to think about the ones that we were looking at in the lecture, I think the ones that you're referring to, and I could also pull up the lecture. Are you referring to the one on multivariable? There was a very brief lecture on multivariable. regression?
Yes.
So I think I can best pull this up. Okay, so so we know we've set this up, and we had an example where we set up the multiple logistic regression where we had two covariates, and these happened to be covariates that were dichotomous in nature: vitamin A exposure, yes, no, and then gender of the child. So we're modeling the log odds of death by vitamin A exposure as well as gender. And so I think then if we looked at the simple regression and for both, and then the multiple regression, maybe I didn't use the post-estimation commands, but maybe one that you're thinking of, Dr. Nishad, that we could have done is I could have saved the results of the simple logistic regression from this regression of log odds of death onto vitamin A status. I could use the estimate store and give it a name such as A, so EST store. Then I could run. Is that what you're referring to?
I think you had run it in the when you were explaining univariate logistic regression, I think. And
that's right. When I was doing the demonstration.
Right. You had done, in the stator demonstration, maybe you had run the goodness of fit command and the. I think you had run the goodness of fit command for Hosmer-Lemaitre. And
that's
the
right.
AIC.
So I would go through all of them. Yeah. So I guess to think about how we might go through this, I'd want to first set up my simple logistic regressions. My first step would be to look at the relationship between the outcome and each covariate of interest in my simple logistic regressions. And I could assess the significance of the coefficient with either a z-test or inspecting the confidence interval. I could move on then to making a comparison. If I have multiple variables, I could set up multiple logistic regressions where we have what are known as nested models. So you might have several different variables, and then you're adding in some other variables to test their added contribution. And so that would be looking at a likelihood ratio test that allows us to compare a fuller model to a model that has only some baseline characteristics. But for each of the models that I'm looking at, I'd be interested in testing the Hosmer-Lemaitre goodness of fit test to assure that they're a likely candidate. And then at the end, if I have several different candidate models, then I could use the Akeike information criterion, AIC, by running that post estimation command as well. So I would follow, from sort of exploratory analyses up through model selection, and along the way, check that the model is providing a good fit and doing some of the things like those assumptions. If you're using continuous variables, can you actually make that assumption that they're linear on the log odds scale?
Well, thank you so
much.
And
then Sumita's asking, can multiple linear regression be useful to test for a causal relationship between independent and dependent variables to test whether an adverse drug reaction to be a cause of intake of a particular drug when the patient's reported to have taken many drugs? So let's just go back and think about linear regression. Our outcome would be continuous, and logistic regression, the outcome is dichotomous. And so if our outcome was adverse drug reaction, yes, no, then we could do a logistic regression and expand that to a multiple logistic regression. But Dr. Sumita, maybe you can let me know, is the outcome you're thinking of the number of drugs? Or see, I'm looking at this as being a covariate, that the number would have the outcome of a drug reaction, then the number of drugs could be a covariate.
Yes, number of drugs. Number of drugs. Yeah.
As the covariate, meaning
Yeah.
the
Yeah.
independent variable. Yeah. So I think this would be a perfect example where we could have a logistic regression that looks at the log odds of an adverse drug reaction as a function of number of drugs. And again, we might want to categorize the number of drugs or test whether there's a linear relationship when using it as a continuous variable. But then you could imagine having age, gender, some other comorbidities that are part of the covariates, looking at that outcome of adverse reaction.
Will it be possible if there are many drugs, say 4-5 drugs? Will it be possible for that?
Yeah, so you could handle this in different ways. If you're interested in in whether a particular drug is associated with an adverse reaction, then you could actually have a coding for this drug A, yes or no, drug B, yes or no. But part of it depends on how many drugs might be taken together, in tandem.
Yeah.
So you might also want to know, combinations of drugs that could be categorized and handled that way, as opposed to just numbers of drugs, because you might know that actually combinations of drugs could result in an adverse reaction.
Thank you. Thank you so much. Thank you.
You're welcome. Oh, good question. Thank you. Dr. Rashmi.
Thank you, Dr. Marie. I would like to ask a question related to the example that you had shown in your presentation.
Yes.
Like when we were talking about these calculations, when we were talking about male gender and placebo. If we
Yes.
want the output for female gender and placebo, would we want to substitute females for 0 and males for 1? Or
Yes.
is there another method?
No, that's exactly right. That's exactly right. And so if you want your comparison group to be the comparison group, this group compared to the, to a comparison group, you would, if you wanted to compare girls to boys, you'd code the girls 1 and the boys 0. But if you wanted to compare boys to girls, you would code it the other way. And maybe this is also where I should pull up the first presentation, and we could just look at that. Or I could do this in Stata, but why don't we try this first? I will share my screen again. Okay. So if we think about setting this up now as a logistic regression, which is coming. Okay, so we used this example, and we were looking at the log odds of death among children receiving vitamin A versus placebo, and we actually stopped with this in this example, and then it was the then it was the multiple logistic regression in which we did the coding. So I will share one more time. Okay, so here is gender, and so we know that the way this is coded was, and we'll just make sure that we look at the coding and the setup. So girls was a 1 and 0 was a male. And so Dr. Rashmi's question was, when we set it up that way, then when we wrote it, if we write out the model, we would be able to see, this was an example where we have X1 differing by 1. So this is where if X1 is a 0, that would be a boy, and X1 plus 1 would be a girl. So that by definition, we're looking at the difference in log odds with beta 1 being the difference between child 2, who is the girl, and child 1, who is coded as 0, which is the boy. So if you wish to change these, you could switch the coding, or let's look at this output. So remember that we said that this B1 is the log odds ratio comparing girls to boys. If we wanted to compare boys to girls, then we would just take the reciprocal of this, right? This is a, in fact, let's look at it in the, let's look at it after we exponentiate it. So I guess I never did exponentiate it here, but let's do it together. So let's see if I've brought my calculator with me, and I have. So if we all look at this coefficient of 0.418365, and if I was to exponentiate that, I would get the odds ratio comparing girls to boys. My exponentiation gives 1.52, but if I took the reciprocal, 1 divided by 1.52, I would see that the odds are decreased in boys compared to girls. So Dr. Rashmi, does that help?
Yes, ma'am. Thank you.
But so you could either, code it differently, and then you would get the negative of this coefficient. So negative 0.4183685. So I don't know how many of you have your calculators with you. But if I was to take the negative of that and then exponentiate it, I would get the 0.658 odds ratio that compares boys to girls.
Right. Thank you, ma'am.
Okay, I'm also seeing some questions now in the chat. So Dr. Venkat, you have a question. The odds ratio is conceivable by thinking of a 2x2 table when the predictor is categorical. And how do you really think of this when the predictor variable is continuous? So you would consider that it's a change in log odds. It's the increase in the log odds for every unit increase in the predictor. And so then if we were to exponentiate the log odds, the difference in log odds, we would get a log odds ratio, in which we would interpret this as the odds ratio increase with every unit increase in the continuous predictor. But for a 2-unit increase, this is a very excellent question, Dr. Venkat. You would want to take the coefficient and multiply it by 2, and then exponentiate to get the odds ratio associated with a 2-unit increase in that continuous predictor. Does that make sense? Here in this crude drawing, you can see the log odds is associated, is the change with each unit increase in age. So if I wanted a 2-unit increase, I'd multiply the coefficient by 2 times the estimate of beta 1, and then I would exponentiate to get the odds ratio. So I hope that helps. And then, okay, so I think all these other questions. And then the difference in the interpretation of the odds ratio as obtained in the case control, there is actually no difference. So the study designs are different. We have cross-sectional is looking at the same point in time. Case control, we're looking at, we've had individuals who have the disease, and we look back at exposure. So do you all remember the property of invariance of the odds ratio? Anybody want to type in what we mean or say out loud what we mean by invariance? It all has to do with it being a 2x2 table, right? Where we have, say, disease and exposure. So because of the study design with a case control study, we're usually interested in what are the odds of exposure in those who are diseased versus not diseased. And so we would typically set up then the outcome to be exposure. But the property of invariance is that the odds ratio, which is looking at the odds of disease in the exposed versus the odds of disease in the unexposed, is the same as the odds ratio of exposure in diseased versus not diseased. So, so Dr. Venkat, I would say that, typically we would
Hi.
say in that way.
Ma'am, hi, Dr. Miss. My problem is that in case of a case control study, we have equal numbers of cases and controls. Say we have 120 on either arm. Whereas in a cross-sectional study, this may not be the case. The number of patients in two groups may not be equal. So
Yes.
this has an implication on, because in case control we select the number of controls, whereas in a cross-sectional study, the numbers may not be equal on both of the groups. So
no, that's exactly right. That's exactly right, Dr. Venkat. In terms of though, sometimes we have in case control studies, sometimes we do have equal numbers, but sometimes we might have a 2-to-1 ratio. So it might be that you have more, controls than cases, and so it could be a 2-to-1 ratio for the total sample size instead. And so
should we compensate? Should we compensate for that ratio in case of cross-sectional? That's my question.
Yeah, so it's a great question. It won't be a compensation that needs to be done in terms of interpretation. What might be the case is sample size, right? So if you actually have this difference in sample size between cases and controls, you might not have, the power to detect, an odds ratio of a certain magnitude. And so that would be what I would consider sort of, a priori, right? In the beginning, when you're designing, your data collection, or considering what you're matching, and so that's another issue. It could be matching. So in the example I gave, these were two groups that were roughly, comparable. But if you had an individual matching on, age and sex and others, then you can do something called conditional logistic regression, where you're actually taking into account that matching.
Thank you, Dr. Best. Yeah, I got it. Thank you.
Yeah, I think that, our interpretation of the odds ratio is the same. It's just, whether or not you have this imbalance, as you're saying, and sample size might influence your inferences. Could change the width of the confidence interval. You're welcome. Thank you. Now, these are great questions. Please continue on.
Hi, Marie. Good evening.
Hi.
This is Dr. Shailaja.
Hi, Dr. Shailaja.
So one of the participants had a question regarding the article, and I thought it might benefit all of us to have a discussion on the same. One line in the article read, the separate age and sex adjusted analysis were also performed. So she was confused as to what it means. So could you elaborate a little bit on that? What do we mean by sex and age adjusted analysis? I think it has already been covered in your last answer, but still.
No, why don't we do this one more time? So I think it's an excellent question that, and it's to the author's credits that they actually discuss or show, that they have done multiple logistic regression with controlling for potential confounders. And so it's the sex and age adjustment. When you see a sentence that indicates these were adjusted for sex and age, that means that they actually were using sex and age as covariates in a multiple logistic regression. So that our interpretation is that if we look among individuals who have the same sex and age, then the odds ratio of the event, in the intervention, I think this was intervention versus no intervention group. Actually, will you remind me of the major covariate in that article?
So it was the dependent variable was in-hospital death, and the various independent variables were cardiac mortality and use of drugs like ACE inhibitors.
Right. So if we put this in the context of saying the odds ratio of hospital death in those using ACE inhibitors versus not, adjusted for sex and age, we mean that we're performing a multiple logistic regression in which we're able to say if you look among individuals of the same sex and age, then this odds ratio is the odds of hospitalization in the ACE inhibitor group versus those not taking ACE inhibitors. So it really is suggesting that a multiple logistic regression was performed.
Precisely. So I would like to point out that I've already posted the screenshot in the WhatsApp chat group, and I've highlighted how do we report this. So the female, I'll just give you a second to.
Right, I'm going to look at my
I would
WhatsApp. Go ahead.
Yeah. So just highlighting the second line for female sex, the odds ratio for dying in the hospital was 0.79, and they have mentioned the confidence interval for the same. So this is how we actually report when we have performed an age or sex adjusted logistic regression. Higher up in the same paragraph, we will also find that they have reported that in age greater than 65 years, coronary artery disease and congestive heart failures, these were the factors that were associated with higher risk of in-hospital death. So the first part of the same, that is the age higher than 65, that is, we are able to get that because we performed an age-adjusted analysis. Now
I
my
wondered, and that's right. So thank you for, go ahead.
No, you go ahead, please.
No, I'm sorry if I interrupted you with that question. I have a different topic I was going to mention based on looking at, but please go ahead. And so your question, the group's question.
Yes. So just in continuation of that, is age adjusted analysis same as age standardization that we perform, or are the two concepts different?
Right, that's a great question. So this term of age adjustment is one that's used in generalized linear models or regression analyses. Age standardization is also a form of adjustment, but it typically is reserved for using, say, comparisons of vital statistics. So we're interested in, after you standardize, it's the same as adjustment, but it's typically used more so in the context of what are the mortality rates, among women versus men if you adjust for their differences in age distribution. So they are the same concept, but we just tend to use this, the term of controlling for or adjusting for covariates when we use generalized linear models, but they are the same concept, yes.
Thank you so much. You were saying something.
Yeah, so what I was I was looking at the tables that the authors chose to give, and I wondered if you had discussion about this. So in the tables, we're looking at survivors versus non-survivors, in two different columns, and then the last column shows not the odds ratio in the confidence interval, but the difference. And I wondered, had you talked about this in your discussion about, certainly the demographics, you see the difference, but then I think if we kept going in the article, they are reporting, so I need to bring up my whole article here, but they're, okay, so Dr. Nishad's saying it was written rather well, but was later retracted. Really? Oh my gosh, did you all talk about this? This is huge.
No,
yeah.
It was big news at the time.
And so where does it stand?
We had thought about, it was the retracted article, but since it did not impact the reporting part and we were concentrating on that, so we did not, we said we'll go ahead, even though the article was retracted from publication.
Exactly.
Yeah, oh my goodness. No, I think, you can definitely have a well written article, but this issue of having, with fabricated data is what, the possibility is. Boy. Anyway, but my question was that I did not, I think that Dr. Shaileja was talking about, the fact that in the text, it indicated adjusting for age and sex, but I didn't see tables that showed, adjusted odds ratios. Did I miss anything?
No, you
Were there
actually did
tables?
not. They have only mentioned this in the text, and one of the participants raised a question about this. So I thought it's better if we discuss with the benefit of the entire lot.
Yeah, no, I'm so glad, because I really think that what they could have done is shown, the unadjusted odds ratio without adjusting for sex and age, and then another column that shows the odds ratio and of course, corresponding confidence interval for the adjusted odds ratio. But we do know that these journal articles are limited in the numbers of tables and figures that are typically allowed. And so that also, might impact it. But I think, good practice would be you can really be very condensed in your presentation style and show both the unadjusted and the adjusted odds ratios and confidence intervals in a single table.
Yes. Might I take the time to discuss another question that is posted by the same participant, because I think it will benefit us all. So the article goes on to
Absolutely.
mention, yeah. So the article goes on to mention that the 95% confidence intervals have not been adjusted for multiple testing, and that should not be used for to infer the definitive effects. So the answer that I had in mind is adjusting for multiple testing is same like doing Bonferroni correction for p-values, so that we can basically limit the possibility of having a type 1 error. But I think you might be able to explain it better than myself, so please do.
Yeah, no, this is a really frequently asked question. And in fact, in the class I'm teaching right now, it's been asked, we talk about the need for a Bonferroni correction or a multiple comparisons correction when we know in advance how many comparisons we're going to be making. And so then we can do something like Bonferroni and take alpha divided by 3 if there are 3 pairwise comparisons of interest. But in regression modeling, we never know really how many variables we're going to be using, how many adjustment variables, how many models we'll be making. And so it is more typical to not perform the adjustment because of the fact that a priori, before starting the study, we don't know how many comparisons we're going to make, so that usually we still report at an alpha of 0.05 without correcting. But certainly if a lot of covariates were used in a model or a lot of exploration, certainly having a caveat in the discussion that indicates that some of these associations may be detected by chance alone because we looked at a lot of comparisons is what I would recommend.
And that will sort of introduce a bias in your study and is actually not encouraged.
It's not encouraged. That's right. It's not encouraged.
Thanks a lot.
You're welcome.
I had a question, Marie.
Yes.
So we always talk about the logit command and the logistic command, and you also demonstrated in the videos that when we use the logit command, we get coefficients, whereas when we use the logistic command, we get the odds ratios. Why do we really even need the coefficients in the logistic regression model, and why do we ever run the logit command when
Right.
we
Great
can directly
question.
do it with the logistic?
Right. So thank you for that question, because you might say, well, why do we have these two commands, and when they really are making the same inference? So the coefficient, our null hypothesis, is that the log odds ratio equals 0. In logistic, we've exponentiated both sides of the equation. So the null hypothesis is that the odds ratio equals 1. So I think that Dr. Nishad gave us the best example of why we would want the logit, and that is because there are certain times we need to examine the coefficients. So that example of the equidistance between the beta, differences in the estimated coefficients if you used a categorical age to do that check. And the other example was, what about the interpretation of a 2-unit increase in the continuous variable. That also needs to be on the coefficient scale and then exponentiated. And so those would be the two examples I can think of. Dr. Ashish, if you can think of others, but in particular, when we're dealing with a continuous variable, we might want to first have it on the coefficient scale because that's what's linear. It's the log odds relationship. The slope is a change in log odds. So any estimated slope or beta is a change in log odds, which is a log odds ratio. That's our interpretation of the coefficient.
Yeah,
but it's a great question because, like, why do we have so many different commands and in Stata? But it's important to be on the coefficient level. So Dr. Susiana asked a different question, and that is how far the difference of the unadjusted and the adjusted odds ratio is accepted, and what's the consequence? So this is a great question, and we didn't talk, in the opportunity that I had, I didn't talk about confounding. And actually, this is another reason why the logit would be important. So there's no real level of acceptability or unacceptability, but if I wanted to answer the question of comparing a simple logistic regression to a multiple one in which we think that the added covariate is a confounder of the relationship in the simple regression, we would look at whether the change in the coefficient that we get from the logit output, whether the change is on the order of 15% or more, 15% or more change in the coefficient. And that would allow us to conclude that there appears to be some confounding. There's some caveats with logistic regression, but with collapsibility, et cetera. But in terms of acceptability, we often are interested in looking at just the changes that we might see. We might see that there's quite a difference, either an increase or decrease of the odds ratio, but there's no real cutoff on the odds ratio itself. It's just that the coefficient change allows us to detect confounding. And so I would go with your suggestion of always providing the unadjusted odds ratio along with the adjusted odds ratio so that the reader can see the difference.
Thank you, Dr. Mary.
You're welcome, Dr. Susiana. And so Dr. Venkat is asking about the term likelihood, and understanding likelihood is difficult. And likelihood is very difficult to describe, other than to say we're trying to look at what's the likelihood of what we observe, and we're trying to maximize the likelihood in order to interpret, in order to get our maximum likelihood coefficients. So we're using a method of maximum likelihood in terms of saying how we're trying to use our data to give us, if you will, the best match to how things work in the real world. And we're trying to then make comparisons often between different models to see those that then will maximize the likelihood that's expressed. But I agree. I wish I could think of a good resource, the best resource to give you for that. So that's what I would leave it at now. And I could maybe try to find some reference, a reference to share with you that I could send, through WhatsApp or through Dr. Ashish. But you're right. It's a little bit beyond the scope. It's a mathematical concept, right? And so it's a little bit beyond the scope of our general.
Sorry for the question.
Yeah. No worries. No, thank you for the question. And then, is there any relation between logistics and the use of the term logistic regression? I don't think so. I think it's just that because it was the log of the odds, log odds, that is how the logistic relationship, was termed. But, we are doing logistics, right? When we perform logistic regressions. I agree, but no, I don't think any relation.
Thank you, ma'am.
Welcome. No, you've been asking great questions, everybody. I give you a lot of credit. You've actually been together now for, isn't this now the 3rd hour? And so really, really good questions.
Yeah, it's kind of great to see that people are interacting and asking questions because
Yeah, no, I thank all of you. This is wonderful.
Meanwhile, we wait for another question. Might I ask a general question about study designs and statistics? It
Sure.
actually popped up in my mind while we were having a discussion on Dr. Sunita's question about causality assessment, or when she asked that can multiple linear regression model be used for to test for a causal relationship. So a general thing that we read in statistics is that the first thing that we read rather is that correlation is not equal to causation. And that is why we always say that you shouldn't interpret like all of these tests and all of the statistics have to be interpreted cautiously. So I was wondering that while we are talking about causality establishment, would the study design have a more role to play than the tests of significance that we are applying?
Yeah, so I totally agree. As you were mentioning this, Dr. Shaileja, is that it's the study design that we're looking at, so in terms of causality, certainly we would say that a prospective study would help us, more with causality. But if we think about the, so there's a framework for establishing causality. Do any of you know this framework? Did you all talk about it yet? Dr. Ashish, was it mentioned?
no, we did not talk about causality yet in this workshop.
So, so let me just see if I can bring this up quickly, if I can. Okay, let me just see if I can. So let's see if I can bring up the Bradford Hill criteria for causality. And I think I can. So this is not the best source, but it's the one that I found quickly. And so, so in terms of, I wouldn't necessarily quote Wikipedia all the time, but so Sir Bradford Hill had 9 criteria to provide epidemiologic evidence of a causal relationship. And so we can see, the strength of the relationship. And so the effect size is in terms of what we are seeing in our statistical association, but it's whether there are consistent, results, so reproducibility, whether there's specificity, whether there's a temporality, biologic rate, and plausibility. So it's really more so all of these taken together that I would stress. And these are influenced by study design. So the temporality has to do with the prospective, study design. So it's all of these. So I'd encourage you, to look at Bradford Hill's causality. And it's really not, it's the study design, not the statistical significance that we're seeing or the statistical methods.
Thank you.
I think Dr. Paramita, so Dr. Shaileja, does that help, or should we have a little bit more discussion about that?
No, definitely that clears things up for me. Thank you.
Okay, you're welcome. So it looks like Dr. Paramita is asking, is the pseudo R-squared value in logistic regression to be given the same importance as R-squared in linear regression? So actually, the pseudo, so anything that starts with the name pseudo I typically don't believe in. But the pseudo R-squared is an attempt to be able to allow one to have that same kind of a notion regarding the fit. But there's much better ways. So I would rather look at the Hosmer-Lemeshow goodness of fit test for a logistic regression as opposed to the pseudo R-squared. But you're right, Dr. Paramita, it's an attempt because it's using R-squared to be able to make a comparison that we see with linear regression. But I'm going to take you back to linear regression and ask, what's the purpose of looking at R-squared in a linear regression? Anybody? What does it remind us all of the interpretation of R-squared?
So in last session, Alden had described it beautifully, and he had emphasized in several of his videos. Yes, Dr. Venkat, go ahead.
So R-square explains the amount or the degree to which the dependent variable can be explained with the available or studied predictors. Say
That's right.
R-square is 0.8, we can explain 80% of the variation in the dependent variable with the predictor studied.
That's right. That's right. And we're able to do that because we know that the denominator is the total sums of squares. It's looking at the variability in the sum of the variability in y about its mean in a squared sense. And so it's a within group. It's something that we would look at within a model to help to do exactly what Dr. Venkat said, look at what proportion of the total variability in the outcome is explained by its relationship with the covariates. So sometimes there's a temptation to look at comparing R-squared across models with different number of variables. And probably Dr. Alden also said, don't do that because this will be artificially inflated just by adding variables that might not even be related to the outcome of interest. So with the logistic regression, we have that quantity of likelihood or log likelihood, and that in and of itself can be, we would expect that the log likelihood would change over different models, but the best is to look again within a model and do something like the Hosmer-Lemeshow goodness of fit test. So I'd advocate that instead of looking at a pseudo R-squared.
Thank you.
So the way this session has been going, I am taken back to my MPH days when you would have a hall of 200 people and a class would have been scheduled for 10 to 12. And at the end of the class at 12 o'clock, you would have a lone Marie standing in front of the podium and a long queue of people waiting to ask questions. And she would keep standing there for hours together, answering all those questions till the very end. And I think that's exactly what's happening here.
No, this is great. I appreciate everyone's, interest in being here. And, Dr. Venkat is saying, the term outcome is replaced by the term endpoint in time to event analysis. And I would say it's still an outcome. So for all of you, you're coming to that pretty soon with Dr. John McGrady, who I know has been working on these slides. And when we think of time to an event, that endpoint is actually dichotomous. So it's going to be time to death, yes or no, failure, yes or no. And so, time to event analysis, unlike logistic regression. So in logistic regression, we say at 12 months, we know the outcome, yes or no for everyone. But when you look at time to event analysis, you'll have studies that recruit subjects at different points in time. You'll have censored observations, meaning they're lost to follow up. They may have had an intervening event. And so, I would still use the word outcome, that your outcome is whatever event, is the time to the event. And so I would use those synonymously. Outcome and event are still the same when you go to time to event analysis.
Thank you, ma'am.
You're welcome.
We've had another participant entering just now, and maybe we could allow her to speak and ask anything which is on her mind. She was taken away a little bit ago, Dr. Asha Tyagi.
Yeah, hi. I'm sorry I was
Hi.
forced to. Hi, I'm so sorry I had to miss out a little much to my own disappointment. I was just wondering, are you aware of a design called sequential allocation studies?
For say that again, sequential allocation?
Yeah, or the up and down statistical method, because in that we cannot do a regression analysis. So lots of times I worked a little bit with this design in my studies, and the common comment I seem to get back is that how to adjust for confounders in a sequential allocation biased design.
And so, Dr. Asha, is the type of design you're meaning is that instead of having, random allocation, it's adaptive allocation, or do you really
Yes,
mean sequential?
okay, maybe I could give an example. Supposing I'm trying to deal with trying to figure out a minimum effective dose as the ED90, then what I do is that in the first, I set a certain starting minimum dose, and then in the sequential dosing for each patient, it is based on the outcome in the previous patient. So if it is a successful outcome, then I decrease it by a certain dosing interval in the second, or I go up. So this up and down kind of thing is it has a lot of different modifications also, this up and down method, and biased allocation is one of them. So the problem is that since you do not have a constant dose, for example, in all patients, then how do you adjust for confounders?
No, so this is this technique of up and down for each patient is not one that I've been directly involved in. I've been involved in ones that have been sequential, but typically the study design has had, say, 8 patients that are at a dose, and then a decision is made to go to a different dose, for another 8 patients. And so that one, you're able to make those comparisons, especially if sometimes you have a placebo, right, versus the particular dose. So I'd have to look this up, but I'm thinking off the top of my head that all that you really now have is one individual who's treated by a dose. There's a possibility of another one because of the up and down nature, correct?
Correct.
So there you might have three individuals treated by the same dose, or does it? Yes. So, I mean, there could be a way in which you actually then are using the covariate of dose, to adjust for. But in terms of this study design, you would not tend to have groups that are balanced in any way.
No,
right?
that is the problem, that those groups are not balanced then. So how do you adjust for the confounders when you do an analysis for the secondary outcome measures?
Yeah, so the best I think one could do is that you have information on the confounders, especially information on what variables are known in advance to be associated with the outcome of interest. And so the best you can do is to actually try to adjust for those confounders in a multivariable.
Sorry.
Say that again.
How could we adjust for those? How do we make those adjustments?
So I think that you defined your outcome, and if it was a 0, sort of 0 not and 1, it could be a logistic. Do you have, when you make that decision to either increase or decrease the dose for a patient, is that outcome that you assessed on the previous patient within a fixed time period?
Yeah.
And is it, a short time period, I imagine?
Yes, it's a point time period.
And so then you could do a logistic regression. The outcome would be success or, not. And then you could adjust for the different, possible confounders in addition to adjusting for dose in your analysis.
Okay.
I think the tough part, Dr. Asha, is that you don't necessarily have all potential confounders, right?
We don't have all of them also, and plus because the dose itself is varying in every patient. So it is not like I have 10 patients with one dose and another 10
Right.
with one. I might have one with a certain dose and I might have 20 with the other dose. So that is where
Right.
the problem comes in, and that's why the bias keeps growing probably.
Yeah, I think so. But I think the best you can do, is just adjust for dose, as well as for the confounders that you have.
Okay. I'll try that. Thank you.
Okay.
And can I ask a very silly question? I've been researching as a clinician for a number of years, but of course I have no formal training in biostats. When we say these are randomized controlled trials, what do we mean by control? You're controlling the environment of the study, or what are you controlling?
So it's actually, you're controlling you're controlling two things. So the treatment assignment is given, in a random fashion as opposed to a biased one. But then you're also getting the benefit of having two groups that are controlled, or in other words, balanced on both measured and unmeasured variables.
So how is controlling then different from randomizing? If I'm randomizing to the two groups.
Right. So if you're randomizing, then what happens is, by the luck of the draw, you're getting two groups that are balanced with respect to age and gender and other characteristics. So the controlled part, is really that you're controlling or adjusting, if you will, for all measured and unmeasured factors. But there's also and so that would be another term for balanced, right? A randomized balanced trial.
So does that mean that my inclusion criteria, exclusion criteria, defining methodology, all this is an attempt at controlling?
No. So the controlled, the randomized trial or randomized controlled trial would mean that you have been able to try to prevent, the differential in characteristics in the two treatment groups by nature of the randomization. But it's not referring to your exclusion, or inclusion criteria.
The term control doesn't mean anything per se, that means. It's just a part of randomization.
It's part of the implication that once you randomize patients, you're going to have these two groups that are balanced or controlled, if you will, meaning they have the same proportion of males, the same age distribution, the same comorbid condition distribution.
Okay. Thank you.
Yeah.
Thank you so
Yeah,
much.
it's just the terminology. So it's similar when you were gone, Dr. Asha, we were talking about the word, of standardizing or adjusting or controlling. They actually all mean the same thing, that we're able to have a comparison of like with like, of apples with apples, because we're able to compare groups that are similar with respect to possible characteristics. So, controlling for, adjusting for are the same thing.
All right, thank you. Dr. Ashish, do I have time for one more question, small one?
Marie would know. I mean, we can go on.
I'm here. So if you have a question, that sounds great.
Okay. When we talk about pilot studies or preliminary studies, is it justified to try and do a hypothesis testing? And if yes, then what should be the alpha error? Should we be sticking to a 5% type 1 error, or should we scale it down?
So often a pilot study might not have a sample size calculation. Dr. Asha, you might say, for convenience, you look at 25, patients in one group and 25 in another. And so it typically is for, the purpose of trying to understand what might be a difference in outcome, based on treatment versus no treatment, so that you can have some notion of what that difference is. You also would have, as a clinician, a notion of whether that's a meaningful difference, And then you
Yes.
can use that to have a larger study in which you now are doing a sample size calculation using that difference as the difference you would be interested in detecting. You know, that this difference or something bigger would be of interest in a practical, meaningful way.
Okay. Okay. Thank you. Thank you.
So I
It's a
think
great
if we
group of
don't have,
people. This
yeah,
could, I love it.
it's also the impact of a great teacher, you know, that inspires the students to ask questions.
Well, thank you. Thank you. But these are really dedicated individuals, you know, I can tell.
Thank you. And I think if we're done with the pressing questions for today, and if there are no more pressing questions, we will let everyone get back to their usual daily grind and come out of the virtual
Yes.
world of statistics. Any last questions? Cool, awesome. So everybody would like to go back and have
Great.
dinner and probably hit bed. Thank
Yeah.
you.
Well, thank you all for, you know, staying with the group this long, and I hope you have a good evening and continued best wishes in the course. So I wish you all the best, and I'm hoping maybe you can bring us all back for a panel discussion or something at the end.
Absolutely.
Yeah.
Absolutely. I would love to do that. We could have the entire panel at the end of the workshop on the last day, and we could have a discussion going. Thank you. Thank you. That would be a wonderful idea. I'll try and organize that.
Thank you. Thank you for all of your attention, and I wish you all the best, and look forward to seeing you in the virtual Zoom room again sometime soon.
Thank you.
Thank you.
Thank
Thank
you,
you.
everyone.
Thank you so
Have a
much.
good
Thank you so
night.
much.
My pleasure, everyone. Take care.
Thank you.